Okay, so in the last section we went over an intuitive approach to the work-energy theorem, but it's not an actual proof. Now I will present to you the proof, but it's going to involve some multivariable calculus. So if you've never taken vector calculus, you you won't understand this part, really. But if you do, or you have some notion of it, then uh, well, continue the video if you want to, of course. I'm not forcing you to watch this video unless I actually am. I was gonna make a joke about like being in your wall or something, but I just realized that wouldn't actually be particularly funny. Yeah, whatever. I apologize. Whatever. Okay. What a weird introduction to this section. Anyways, let's continue. Let's continue with this rigorous proof. So we want to rigorously prove that one half times the mass of our object times the difference in the squares of the velocities at the extremes is equal to the line integral of force with respect to position, to our position, to our position, yeah, position vector, which will be expressed in a small differential displacement. But to actually prove this, we're going to need to use something called a parameterization. So in order to prove this, we really only need to look at only going to look at the right hand side of our equation. And in order to prove that our right hand side of the equation equals our left side of the equation, it equals to the change in kinetic energy, we're going to have to introduce a concept called parametering. Oh god, I cannot speak. Parametering. Um, parameterizing the position and the velocity of our object. So what I mean is that our object is traveling along a path C. It's any path. It could be in 2D space, it could be in 3D space, whatever. I mean, if you really want to generalize it, it can be in any Euclidean space, like I don't know, four-dimensional space, whatever. Sorry, but attachment doesn't matter. But pretty much, it's traveling along some path C, and C connects 2 points. It connects point x0 to point xf, and it's oriented in the direction of x0 to xf. To simplify things, we can represent these points as vectors in space. So now let's assume that our path is smooth, it's continuous. It will be smooth, it has to be smooth, or else it wouldn't make any physical sense. So since that's the case, we can parameterize C. And what that means is that there exists some function R2, not R2, RT, that we can take to be, it's a vector quantity, that we can take to be our position vector for any t. And R is a function of t, and we define ti and tf so that r of tf is equal to xf and r of ti is equal to x naught, x0, whatever. And this also, if we differentiate both sides of this equation with respect to time, this also implies that the time derivative of r is equal to velocity. So now we can rewrite our right-hand side of the equation into something that's actually manageable using r. This step right here is a bit unrigorous in the way I present it, but you can actually, if you know the definition, like the Riemann integral definition for line integral, you know, like an infinite sum, and then the sum is put under a limit, you can prove this by yourself. In other words, I do not think that I would have to prove this, and I'm too lazy to restart the video, to restart this section. So, tough luck, buddy. Whatever. So, anyways, we can rewrite the right-hand equation. So, you know, the right-hand equation is the integral of effective position. We can write it in terms of integral with respect to time, to t. You know, the independent variable of our parameterization of position. In this case, we can actually put definite boundaries on this variable, on this oh god, definite boundaries on this integral. Oh my god, I'm so sorry. Ti, that should be tf. And then using our previous definition of velocity, we get this. And now we can further rewrite this by taking out mass, and we get this. I should have mentioned that the second time derivative of r is also the acceleration of our object, so we can rewrite it as this. Okay, nice. So we have this new representation of the right hand of the statement of the work-energy theorem, and this representation right here is much more defined, so it's much easier to work with. And if you're you can see, if we look at what's inside here, this is actually just the time derivative of the first derivative of r dotted to itself. Yep. And using our previous definition, that is actually equal to the time to d over dt of velocity squared. So let's just put this in. We get m df di. Oh yeah. Oh, sorry. We get it's 1/2. This quantity right here is equal to 1/2 of. It's equal to this. It's equal to 1/2 of the time derivative of first time derivative r dotted to itself. You can see if this is true. You can easily see that this is true. You know, just take a piece of paper and write it out. Okay, so whatever. Let's continue. So we get this, yeah, and let's put this on new page. We've managed to, using that equivalence between two different derivatives, we also have this expression. And this is simply, this is just a fundamental theorem of calculus. It's the integral of a derivative. So that's simply the difference in the parent function, which in this case is the derivative of r dotted to itself. So this is simply 1/2 rt dot rt evaluated between these 2 points of time. And this is simply and let's see. If you know, then okay, I kind of made a big mistake for this entire video. In the original statements, I put this. This is not the full picture because v, you know, it's a vector. You can't just square a vector. It's much more reasonable. It's actually more accurate to say v dot v or 1/2 times the square of times the change in the square of the magnitude of velocity, and that is also just equal to v dot v. So similarly here we can rewrite it as evaluating this integral. Get that it's 1/2 m times the quantity of the square of the magnitude of the first derivative r evaluated at tf minus the same thing but evaluated at ti. And I forgot to write this again at the very start of this section, but or the derivative r, it's a vector quantity, evaluated at tf is equal to v at the velocity at tf, and that's similarly true for initial time. Let's see. It's better to write it as this. And so looking back at this absolutely horrendously organized page, we can simply rewrite that representation of the right hand as this. And if you're willing to abuse notation, you can just remove the magnitude sign and you just get vf squared minus vi squared, which is equal to, you know, that's a change in kinetic energy. And this is a more rigorous proof of the work-energy theorem. There's a few steps I skipped. There's a few assumptions I made. They were still very reasonable, but maybe I can't really say they're exactly rigorous. And the big step that I skipped over in terms of rigor is this step right here. But you know, it's just use the classic, the absolutely goated method in calculus in deriving expressions or equalities. Just treat differentials as fractions and cross them out, and then you can see these two sides of the equation are pretty much the same thing. This, of course, is not, you can absolutely do this always. It's not like a mathematician dies inside every time you do this, as I am right now, but I'm not a mathematician. I'm just a high school student who's pretending to know what he's talking about, but this video kind of disproves that, but whatever. Yeah. So this part of proof, yeah, it's I did not really prove this, but if you know the definition of triangle, you can prove this. But I'm not going to because I kind of forgot how to. Oh yeah, sorry for that, but you probably heard that. Yeah, but yeah, that's the video, I guess. Thanks for watching. I might do some more videos like this. Hopefully they'll be better next time. I'll probably do them in calculus, physics, both physics, mechanics, and E&M. And I might actually do some on statistics and biology. Yeah. Yeah, so thanks for watching.